Hey, welcome back to week 9, lab 9. We are going to continue on with our analysis. So far, we have established our question. We have this imaginary cousin that wants to decide what major she should go to at university, she should pursue at the university. She has two constraints she's playing with: her interest in quantitative sciences like computer science and physical science, and her wish to pursue a career that will pay really, really well. And she puts the pay constraint first, and the second, how much she likes it. So we want to use data to help her make a decision. We decided that because we're comparing 3 different major categories: engineering, computer science, and mathematics and physical science, that we need an ANOVA because we're comparing 3 means, more than 2. So we went through the process of confirming that we meet the assumptions for running an ANOVA. So we're done, we meet the assumptions, we're good to go. So the first step in actually, going through the analysis is doing a formal descriptive analysis of the data, figuring out what are good numeric summaries for the data and good image summaries for the data. So let's try to do that. So I'm going to suggest that we get, and you're used to this because we did the same thing for the t-test. We're asking R to open up the data set, just data cropped, and then keep it open, right? So you keep the output of one command when you pipe, and the next command uses the output of the first command. So the output of the first command is just the data set. And then we ask R to group by major category and keep that grouping. And then we ask R to summarize these different groups and get the number of participants in each group, the number of majors in this case in each group, the mean of our response variable, which is the mean of the typical salary, the standard deviation of the typical salary, the standard error of the typical salary, and I also asked for the confidence intervals around the mean for the salaries. I'm using a z-critical, the 1.96, which is the z-critical that's related to the 95th percentile. So we're doing the 95% confidence interval for each mean, right? So here we go. We press run and we should see a table like this. And by looking at the table, we see that engineering clearly has the highest typical salary, followed by computers and mathematics, and then physical science. Now, of course, while summary statistics, like numeric summaries, are helpful, we can actually look at the values. They're not the most compelling way to present the data, so we can create graphs. And again, this is the bar plot. I'm not going to go in detail over it again. You can look at lab 4, or you can look at last time. I went piece by piece. What are the things that need to be changed? I expect that by now you can locate those things. So briefly, you want to make sure you have the right data set, you have the right thing on the x-axis and the right thing on the y-axis, and those things need to be named in a way that is absolutely matching. The name of the data set can't have like capital letters. If it's not capital letters, any typos will throw you off. And the names of the variables within the data set, not the conceptual meaning of them. R doesn't know that, but however they are called inside the data set. Everything else can stay the same, and then you can change the titles, and that's it. And if you plot, we can very quickly, in one glance, kind of get the feeling for, engineering will get the high salary of all. Now, what we don't know is whether this difference in means is actually just a product of sampling error, and then that means that the null hypothesis might just be true. There's nothing going on. There's no relationship between the major categories that we're looking at and the salary. Or it may be the case that it is meaningful, it is reliable, and it's not likely for us to see these differences under the null hypothesis. So we need inferential statistics to figure out whether this pattern here that we're seeing, we should trust or we should dismiss as just sampling error. So the inferential statistics requires us to set up hypotheses. The null hypothesis is that the mean typical salary, the median salary of engineering equals that of computer and mathematics and that of physical science. And the alternative hypothesis is at least 2 of these means are different. We're going to run now the ANOVA in R. And we will use, I said, this will concentrate on AOV, but I will actually use another one, which is LM, the LM function, which is the standard method to run. And it's actually going to be better to use this function versus AOV, because when we learn regression, we'll basically keep the same function. So less things to learn. Like t-test, the LM function asks us to enter our dependent and independent variables into the model. In that little style that you just learned, you have the DV, or the response variable, squiggle, and the squiggle in the middle, and then your explanatory variable or independent variable, and then the data set. That's all. It's even easier. That's all you need to put in. Okay, when you're running independent ANOVAs, simple ANOVAs, I mean. To print the output, there is just one more step. So here, what we're doing, we're basically getting the model, and here we're asking R to print the output. So if we do this, we get the output that you've seen in our lecture videos. So you see that this is the group, the major categories are group this time. The category is not social class, it is major category. We see the degrees of freedom. So we have 3 major categories. 3 minus 1 is 2. We have the sums of squares of the group. We have the mean square, the F ratio, and the p-value. And we have that for the unexplained variance. What we don't have here is the total variance. But as you know, you could just sum these 2 and you would get there, right? The degrees of freedom of the total variance would be 49, which is 50, number of observations minus 1. The mean square is also just the difference, just the sum of these 2 would be on the bottom line. Anyhow, question: what decision would you make with respect to the null hypothesis? And now I'm going to go to the key because I don't want to waste your time writing. So let's go here and find that question. What decision would you make? So the decision is based on what you're looking here, the probability of observing this F ratio or higher. If that probability is very tiny, we assume that the null hypothesis is not true because it's not likely to observe such a high F ratio, which suggests that there is much more between groups variance than within groups variance, right? So it's useful to have these 3 means to capture our data, which suggests that there are differences, at least 2 of them are different. And the probability is less than 0.05, so our decision here would be to reject the null hypothesis. And what's the interpretation of the results in the context of the data? The median salary an individual gets is related to their major categories. At least 2 major categories differ from each other out of these 3 we are analyzing in terms of the median salary. Why can't we say more than this at this point? Well, remember that the null hypothesis of the ANOVA test, of the omnibus ANOVA test, this test that we just ran, is that there are no differences between observed means. Look, engineering equals computer and mathematics equals physical science. No difference between anything. They're all the same. But it doesn't tell us what those specific differences are, right? So our significant result then, because the null hypothesis is that everything is equal, if you get a significant result and you reject that hypothesis that everything is equal, we still don't know where the difference lies. Every mean could be different from each other. You could have just one pair of means that's different. We don't know. This suggests that we need more testing, right? This tells us that we cannot stop here if we would like to locate where these differences lie. I mean, here it's really important because of the kinds of questions we're asking. It's not sufficient to just say, nope, they're not the same. Okay, they're not the same, but what does that mean? Is engineering different from both my preferred majors? Or maybe engineering is different only from physical science, not computer science, which means if computer science and engineering is about the same in terms of salary, I can pick my preference, right? So I'm thinking of the cousin. So it is important in this case, not always it is, but in this case, it is important to know which particular major categories are actually different from each other. To get that answer for the cousin, we need methods of pairwise follow-up comparisons. And just know that the number of comparisons you make are related to the number of hypotheses that you need to test. Because we have three major categories here, we basically have three comparisons. Computer and mathematics with physical science, computer and mathematics with engineering, and physical science with engineering. Three comparisons total, and we have to set up null and alternative hypotheses for each one of those comparisons, right? So null hypothesis 1 would be that engineering and physical science are the same, and the alternative hypothesis 1 would be that engineering differs from physical science. Hypothesis 2 would be that engineering is the same as computer and mathematics, and the alternative would be that it's different. Hypothesis 3, is that the mean median salary of physical science equals computer and mathematics, and the alternative, H3, is that they're different, right? So how do I test this? We have some options, and you have to pick the best option when you are doing your independent activities and your exam. So let's look at this. LSD is one of them, and we said this is the least significant difference, and it's the most anti-conservative as it provides almost no protection on type 1 error, but it's used as the Bayes pairwise method for other approaches. It basically uses the t-test, as I said in class, but it changes in that the denominator of the t-ratio will not be computed in the same way that we compute the denominator, which is the standard error, for the t-test. We'll use the mean square error that is in the ANOVA table, all right? So when we run, what we have to do, this is the Bayes code if you want to run an LSD, the least significant difference test. You set up your LM model because you're gonna need it. Then you, as an input to the function LSD test. So the LM model is one input. And then we say the TRT is which major, which is the category that you want to then do the pairwise comparisons over, which is major category. The error degrees of freedom to set up our F distribution. Our T distribution here is this one, the error degrees of freedom of the ANOVA table, to select the T distribution that we need. The MS error, we need to grab from the table here too, which is this guy. So I copied and pasted here. The alpha is 0.05. And these things you can keep fixed. On the next video, I will explain what they mean. But when you run this, what you get is basically all the comparisons that you need. We have computer science, computer and mathematics versus engineering. Different. Computer and physical science, not different. Engineering and physical science, different. And we know the direction of the difference. Here is computer minus engineering. That's why it's negative, because engineering is higher. And we know it's higher also because we did our descriptive statistics first. So we have engineering better than computer, engineering better than physical science, and no difference between computer and mathematics and physical science. When we get back, we'll dig into some of the other inputs that relates to how this output shows up. See you then. Bye-bye.